and I'm going to get rid of this. All right. Thank you. This presentation is very much an interpretation of the data sets collected as part of the Cloncary Metal project, and I'm going to focus on the Ernest Henry deposit and particularly on the mineral zonation at the Ernest Henry deposit. So for the most part of this talk, I will try and combine modal mineralogy determined by TEMA with the results of detailed petrography and data collected using some handheld tools, such as the portable XRF or the gamma array spectrometer. This is to set the scene for some sort of a new mineralization model at Ernest Henry, which is entirely evident from the data of the Cloncary Metal database. So far, we saw many data sets providing regional expressions of mineral systems. Okay, and in this talk, I want to shift the focus slightly to the drill target scale. So the scale where probably most of the exploration money is spent. I will touch during this talk a bit of just briefly on the geology of the Ernest Henry deposit, and then we jump straight into modal mineralogy and look at the results, and then we combine sort of these sample scale results into an alteration mineral zonation, and then we try and link this data among different different data sets and come to a couple summary slides. I don't want to bore you too much with this synopsis of iron oxide copper gold ore deposit features, because you probably have heard in many talks over the last, let's say 2 years online talks, but I want to focus on this zoned alteration and particularly on this hydrolytic or acid alteration, which becomes more and more evident to be present at Ernest Henry. Brief interpreted geology of the Ernest Henry area. I don't want to bore you too much with it, but we heard already the ore body sits in sort of a magnetite K-feldspar alteration envelope, altering sort of intermediate metavolcanic rocks, a few intermediate metasediments, etc. So let's focus on Ernest Henry. On the right, you have a sort of a representation of, I think, the 1% copper ore shell at Ernest Henry with the pit outline, and then the sort of the orientation of 8 drill holes, or drill holes intersecting the Ernest Henry, or partly intersecting the Ernest Henry ore body. And so we distribute, more or less regularly distribute 270 samples among these 8 to 10 drill holes. And we will focus on one drill hole. So I'm going to show you results from one drill hole just because the others more or less show similar things depending on where you sit in the alteration envelope. So we're going to look at data from this sort of drill core, EH691. On the right here, you have you look at the scanned sample surface. So this surface was scanned by the SCM TEMA approach, and so the sample diameter is roughly 2.4 centimeters. And on the right side, we see the mineral abundance of the entire data set from Ernest Henry. So incorporating mineral abundances from all drill cores, or from samples from all drill cores. And if we look at these sort of general abundances, we see minerals which are very abundant in bold. So these are greater 50% of the samples show, for example, K-spar larger than 0.05 volume percent. And then on the other hand, you have minerals which are abundant or even present. For example, fluorite is present in less than 10% of the samples. So what is this about? So we basically took the published sort of database and started to work with it. Okay, and this slide shows now 49 samples from drill hole 691, and what we're looking at is basically a downhole plot of these samples. So roughly 500 meters interval with the sample number. Then we have a structure, okay, that is from the geological logging database with marsh shear zone, hanging wall shear zone, footwall shear zone, and the break shear zone. And then on the sort of x-axis, we have lithology, the alteration footprint, which we leave for the moment, and then we have a range of minerals or groups of minerals. And in this plot, we see basically a number for the volume percentage for each mineral, and a color code, sort of like warm red colors indicate high values. So, and it doesn't really matter whether you see all the numbers. What I want you to see is that in this sort of representation, we see a broad mineral zonation, okay, towards the ore body. So the ore body is expressed by this chalcopyrite, okay? And the second one I wanted to show is that the ore body shows sort of mineral halos of individual minerals, just for example, pyrite, but also apatite, extending tens to hundreds of meters beyond the limits of the ore body. If we switch to the top part of the thing, we see the known sort of mineral alteration zonation, albite, scapolite, dominant rocks, grade into some sort of biotite, dominant rocks or bearing rocks, then into K-feldspar, and then chlorite comes in, and then sort of at the boundary zone on both sides of the ore zone, you see an increase of white mica. Another interesting mineral here is quartz. So we see it's a bit patchy, but I think one does see that the general increase of quartz towards and within the ore body. And then in the ore body, we have a few occurrences of barite and fluorite, and again, these broad alteration halos of some minerals that are actually relatively easy to recognize, either by geological logging or by portable XRF, as we will see. So let's have a look at some mineral maps or some petrography of this distal alteration footprint at the top. And we see lots of basically an albitite with magnetite, in this case, cross-cut by a magnetite calcite vein, a bit of pyrite, a bit of actinolite, but nothing major, let's say, spectacular from a copper point of view. Certainly the distal alteration footprint. If you go closer towards the ore body, and we sort of switch towards magnetite and biotite, replacing the albite altered rock, so that goes towards the potassic alteration. So we see a biotite integral with magnetite, a bit of titanite, etc. And the beauty of these mineral maps that you actually can do petrography, you can establish the timing relationship, what's actually happening on the way towards your ore zone or your drill target. Here we see we sort of in the middle here somewhere. We see early albite replaced by K-feldspar and then late infill of calcite. There's not yet any chalcopyrite, but this is sort of the classical interpretation of sodic, one sodic alteration, second, or replaced by potassic alteration, in this case K-feldspar. Let's have a look at another sample that's sort of a close-up from this one here, and this really stresses that the timing relationship that you see during petrography. You see here in brown biotite, sort of cross-cut by chlorite, basically chlorite replacing biotite. And this is it's probably one of the most abundant observations in petrography in drills, in samples from Ernest Henry. And we'll come to that. If we go to the marginal ore zone, we see lots of evidence for hydrolytic alteration. So for those of you that don't know or don't remember what it is, it's basically the reaction of minerals with an acidic fluid. In that case, the replacement of K-feldspar by white mica. And it's important that this reaction is actually quartz conservative. Okay, so that the quartz is going to be redistributed, but it's not adding or leaching anything out of it. What we also see is that it's quite a bit of apatite. In one of my talks a couple of weeks ago, there was the question is what's the importance of apatite, or what does it show? Because we really see that the apatite is probably a mineral that when you can recognize it, it potentially or when you can maximize it, you have a higher chance to see higher chalcopyrite grades. And this slide is not from Ernest Henry, it's from a IOCG prospect in South Australia, Triton. It's some sort of near prominent hill, and this shows basically that this replacement of feldspars by apatite is not unique to Ernest Henry. It's a very common thing that we see in quite a few IOCG deposits. What we see is a chlorite and cerussite altered plagioclase, crystal, and in that case it's chlorite, a bit of quartz, and lots of apatite forming within the altered plagioclase, and down here as well, so heaps of apatite at the position where feldspars or plagioclase were originally located. Let's go back to Ernest Henry. And so what this apatite actually shows, or trigger, or what it actually shows is it's an indicator for replacement of aluminosilicates such as feldspars. And when all of it is gone, okay, replaced by alteration mineralized damages such like chlorite, or in that case iron oxides and quartz, you get a lot of apatite. And this is sort of from a sample from Ernest Henry in the central ozone, I believe. So, but the point is here, when all of it is altered, nothing is going to buffer the fluid, whether in redox or in acidity. So you want to have a rock that still contains some of this mineral assemblage that can buffer fluid acidity. And in this case, there are remnants of K-feldspar chloride, lots of magnetite and redistributed quartz, and you see the chalcopyrite is sort of infilling these wax in between. Let's so far I've presented SCM TEMA, also modal mineralogy data, and now we try and link this modal mineralogy data with data from magnetic susceptibility and portable XRF and radiometrics. And what we see here is again sort of a summary of the mineral zonation, so alteration compositions for, let's say, feldspars, so all of feldspars taken together, summed up to 100%, and they're not represented in this 100% staked bar plot. We see an upper part is essentially albite altered, then it sort of transits into K-feldspar altered zone, and what we also towards the ozone, and what we also see is at the bottom is actually not albite altered. So a rock with K-feldspar, plagioclase, and albite sort of represents the feldspar composition of at least or not really altered bit of metavolcanic rock. I showed you the replacement of biotite by chlorite, and this is now again over the 500-meter interval with roughly 15 meters interval between samples. You see a broad zonation of biotite, and then the biotite sort of gets replaced by chlorite and white mica, so a beautiful, nice zonation across hundreds of meters. And especially if you're able to track these sort of mineral assemblages and you see gradients, then you can basically close in towards higher grade. This is something that Courtney has touched on this morning. We see a ratio or a significant change in the chloride chemistry from magnesium-dominated chloride in the distal part towards iron chloride dominated in the sort of central, sort of marginal ozone, and then back to magnesium-dominated chloride in the central ozone. I touched on the quartz amount, okay, and if you look at the rocks, then I had presented you that there is an increase of free quartz towards the central ozone, okay. That's this one. But when we look at the silica content, it's actually fairly stable, and or even might be slightly decreased towards the ozone. We see the broad sodic and potassic alteration envelopes with albite at the top, but this is from assay data, and from potassium over aluminium, basically the indication of K-feldspar alteration. And what is important here, if you sort of take portable XRF measurements, recurrent portable XRF measurements, and you look at phosphorus, manganese, arsenic, uranium, and uranium from the radiometric measurements, then you sort of see a gentle but general increase towards higher copper and gold grades. And this is something, and I repeat myself here again, is that extends over hundreds or dozens to hundreds of meters beyond the limits of the ore body. But this is something, really something that one can measure with a handheld tool. I think I covered that already. And now we're going to take took the entire database or selected stuff from selected values from the database, fired it up in Leapfrog, and then exported it to make some sections. And this is what we see here is a section representation to the Ernest Henry ore body. We sort of in the background, you see sort of the simplified geology. White would just mean the metavolcanic host rocks, with sort of different albite alteration, etc. And then here, sort of in the lines here, the colored lines are the copper grades, and then plotted are some results of the that are stored in the database. And we see, we see sort of the iron oxide composition, and then that goes. And then the degree of hematite overprint of magnetite that maybe answers some of the questions that Leon had in the chat. So we see towards the ore zone, we see a general, not too big, but a general replacement of magnetite by hematite. And this is also the sort of the zone where the magnetic susceptibility goes down and the copper kicks in. And all of these data is basically portable XRF data and from the Maxus handheld tool. And this nicely correlates with the sort of overall copper grade distribution determined by assay data. And now we can also put the mineral assemblages into 3D in Leapfrog, and most likely also in the geoscience analyst. It's a bit of a tricky thing, but it's possible. If you want to do it, please talk to me. I use something that I can connect with Leapfrog, which is Imago, and it's not that straightforward, but it works actually fairly well. So you basically get then the 3D, and in this case the 2D representation of the broad mineral zonation, not a mineral zonation that is not one mineral, but the groups of minerals. So you see albite altered, basically not albite altered, and the core is sort of K-feldspar altered, and this is sort of seen across the entire ore zone. If we look at the biotite chloride white mica distribution, we have looked at this. Then you see basically that this sort of replacement of biotite by chloride is not only seen in this one drill core, it's also seen in other drill cores when you go closer towards the high-grade ore zone. And this is an expression essentially of this hydrolytic alteration. So let's look at the hydrolytic alteration with just three sort of reactions. I don't want to bore you too much with it, but what we actually see that the magnetite towards the ore zone is slightly to strongly replaced by hematite, and this is in essence acid fluid neutralization reactions, transforming magnetite into hematite. A similar sort of acidic fluid can transform biotite to chloride, and as I said, this sort of reaction is responsible for the redistribution of silica into quartz, but it's overall a quartz conservative or silicium conservative reaction. The same thing is sort of can be seen with the replacement of K-feldspar by muscovite and quartz. Again, the feldspar, K-feldspar reacts with an acidic fluid to form a phengitic white mica and results in a redistribution of quartz. This slide shows the sort of a combination of different data sets. On the right ternary diagram, we see the mineralogy derived by SCM-TEMA with biotite and enite summed together. And we have chlorite and muscovite plus phengite. And the color code represents sort of the position of the sample within the alteration footprint. So purple is samples from the central ore zone, whereas blue are samples from the distal alteration footprint, either at the very top of drill hole 691 or in the region. And the important part is this is sort of samples from the entire Ernest Henry data set, so roughly a number of samples. So we see that sort of the medial alteration footprint with what we have heard in the morning and Jim, you see biotite and albite dominated mineralogy in this sort of expression. And as you go towards the ore zone, you would increase the amount of white mica and then certainly chlorite in the central ore zone. And again, this is sort of the magnesium dominated chlorite. And now let's compare this with the results from the portable XRF measurements and the whole rock assay data. And here, this is actually, it sounds trivial, but it's actually quite an important conclusion I'm going to make. So when we look at the portable XRF data that has been collected on the same sample surface as the SCM-TMA-derived mineralogy, we see sort of the same shift towards white mica and chlorite dominated assemblages within the ore zone. If we compare this with the results of the assay data show that the ore zone is essentially K-feldspar altered. And yes, it is K-feldspar altered, but the clasts are K-feldspar altered, not the matrix. The matrix is chlorite and white mica altered. And why is there this discrepancy between? It is simply because the volume of the clasts impose their chemistry on the assay data. So this is a potentially really important conclusion because the assay data is most likely not able to see the effect or let's say to see the subtle effect, but really important effect of the hydrolytic alteration. The hydrolytic alteration is seen when you look at the scale of the mineralization, which is the scale of the breccia matrix. That's a very important conclusion. Let's have a close up with the relationship of the footwall shear zone to mineralization. And we have three images here, and I think one can see that it's sort of a sheared metavolcanic rock, highly potassic altered with a bit of white mica. And that's for 3 samples for 1 drill hole, and sort of both samples around the ore zone so show this sort of shearing texture, and actually the 5% copper breccia in the center doesn't show this. So there is no orientation or visual orientation of this shearing left anymore, and this is because the mineralization, the hydrolytic alteration, overprinted or postdated the shearing along this footwall shear zone. And once you replace the K-feldspar, or once you destruct the K-feldspar, you basically result with hematite, magnetite. You redistribute the silica into quartz, and you allow porosity to be infilled with chalcopyrite. And this is, I think, is my third last slide. So this is sort of a tentative mineralization model. For those who have rotten tomatoes, it's the time to smash them towards the presenter. I'm glad I'm sitting in Perth here. But what is I'm taking the conclusion of Jim Austin and Helen McFarlane in one of their reports. So a developing northeast, opening of a developing northeast trending jog. Okay, and then alteration kicks in, and we leave the fluids out for a moment. But you see sodic plus minus iron plus minus calcium chlorine alteration and the formation of albitite, magnetite, scapolite, just as I presented at the top of this drill hole EH691. As you have continuous shearing, that's certainly an interpretation. Continuous shearing, you start to overprint K-feldspar, magnetite, apatite alteration. This sort of alteration overprints the biotite magnetite. Evidence for this I have shown you in the TMA sections. And so you go towards the hydrolytic alteration, and this sort of Mickey Mouse interpretation shows the effect of the hydrolytic alteration on the earlier K-feldspar chlorite alteration. So that we have pretty acidic fluids that start to replace predominantly smaller grain sizes, or basically the breccia matrix by chlorite, muscovite, quartz, and then eventually into quartz, chlorite, hematite, phengite, chlorite, calcite, fluorite, and in the center, barite and apatite. And this is also responsible for some classed etching that you see and that I have presented in hand specimen and in the TMA maps. And then once this is sort of goes towards more increasing hydrolytic alteration, you make the room for the mineralization of copper and gold in the central parts of the ore body. So this is more or less, taking a bit too much time here, so let's jump to the final slide, or the second final slide. So some of you might have seen this sort of slide already. And I'm going to scale out a bit to several IOCG deposits worldwide, and we see the effect of hydrolytic acid alteration certainly in Olympic Dam and Prominent Hill, and this sort of slide here needs to be redrawn because it doesn't show the effect of hydrolytic alteration. But when we take these together, we have now in all major IOCG zones, we see hydrolytic alteration responsible or sort of related to copper mineralization. The last slide, the Ernest Henry deposit shows a distinct alteration mineralization, which can be explained by a sequence of iron oxide-alkali-calcic alteration, and as I stressed in this talk, superimposed by hydrolytic alteration. The hydrolytic alteration is likely involved in chalcopyrite mineralization, and from an exploration tool of perspective, the SEM-TEMA technique accurately maps the zone hydrothermal alteration and allows vectoring towards the mineralization. So when you're able to analyze the mineral assemblages as a known, then this can be used to close in towards higher copper grades. And handheld tools such as portable XRF and the gamma ray spectrometer, if you can measure uranium, manganese, phosphorus, and arsenic with recurrent measurements, and combine it with SEM-TEMA analysis, and then this might be a way forward in early IOCG breccia and drill target evaluation. And I thank you with this slide, selected references. And if you have more detailed questions about this, whether it's to the geophysics part, or the mineralogy, or the structure, just give us a call. We're happy to help. Thank you very much.